Hi there. My name is Vincent, and this is my submission for the Summer of Math Exposition. The video that you're about to see originally appeared on the Calm Code project, and if you're interested, you can find all the code on that website. However, I also decided to add it onto YouTube such that people can discover the content here as well. The content is exactly the same, with the only exception that on the Calm Code website, I typically only host very short videos, and on YouTube, I've pasted all the videos together, which can be good to keep in the back of your mind.
In this series of videos, we're going to be talking about a thought experiment. Let's say that we have a lot of people in a country, and let's say that some of these people carry a disease. Maybe, let's say, 1% of all the people have this disease. Well, then one thing you would like to do is you would like to test. Does this person have the disease? Does this person have the disease? Etc. And let's assume that we have a test that's actually super reliable. Then we might still have one other problem. It might be the case that we have a lot of people in the country, let's say 1 million people. And that would mean that we might need 1 million tests in order to test everyone. That is, unless we introduce a property about this test. What I'm about to suggest isn't necessarily reflecting of medical science, but for the thought experiment, let's say that we can group people together. What I then might do is I might say, okay, let's get a blood sample of every person in the group. Let's put all of that into a test tube, and then we can test just this one vial to see if anyone in the group had the disease. And it might be the case that I can confirm that, hey, this group is fine, and so is this group. The only downside is that then if I get a positive test, I don't know if it's one person in the group who got the disease or if it's multiple people. Given this thought experiment, the question now is, how many tests do we need to test everyone? And also, what's the optimal strategy when it comes to making groups? So at this point, what I'm hoping is that you're interested about this thought experiment. Again, I don't want to suggest that this is in any way related to the medical field, but as a thought experiment, I do think it's an interesting system to study. And in this series of videos, I want to explore the system that is behind this problem, but that's really only one of the goals that I have in mind with this series of videos. The problem is interesting, and for sure, maths will play a role in understanding this system, but formulas alone won't be enough if we want to gain an intuition on what exactly is happening. It'd be better if we could explore the system interactively, which also means that programming is going to play a role here. And I really want to emphasize this, because in my career I've met a lot of really smart and clever people who taught themselves programming, but never had a formal education in maths, and therefore have always found maths to be rather intimidating. At the same time, I've also met a lot of folks who studied mathematics, and who are very comfortable writing proofs, but who are always intimidated by programming because you have to set up environments, and it can definitely be intimidating too. So in this series of videos, I want to explore the system by walking the middle ground here. The idea is that I will be using both mathematics and programming to explore this thought experiment. The mathematics will help us in thinking systematically, but the programming is definitely going to help us gain more of an intuition, and as I'll show, the programming can also help us deal with some of the harder mathematical bits. This will also allow me to demonstrate some amazing tools from the Python ecosystem, but it hopefully also inspires some cross-pollination of skill sets from different backgrounds. So, I'm interested in finding a strategy to group people together such that we need to spend as little tests as possible. As you might be thinking, there are a couple of moving parts to this puzzle, so it helps to structure our thoughts a little bit. I'm about to explain my thought process, but this might also be a really good time for you to pause the video to ponder yourself a little bit about this problem. Here's my thinking though. Whenever I'm presented with a puzzle like this one, I always try to think in extremes. So what would happen if I make one really big group? Well, we could assume that everyone's blood sample is going to go into a single vial, but if this group is really big, there has to be at least one person who has a disease, and then this exercise is not going to teach me anything. The other extreme might be that I make groups of exactly one person. And here you've got the opposite problem. Sure, you're going to know for sure whether or not this person had the disease or not, but now you're going to be spending a lot of tests. So the solution is probably somewhere in the middle. Having said that, let's see if we can come up with a property that we like seeing in our groups here. Since I'm interested in spending as few tests as possible, I feel like I'm interested in constructing these groups in such a way that I can send as many people home as possible. So maybe what I'm interested in is kind of a probability of sorts. I'm interested in the probability that nobody in the group has the disease. If no one in the group has the disease, then the group will do one test and then everyone can just go home. This sounds like a good idea to formalize, so let's do that. When do we have a group where no one has the disease? Well, if I take this as an example, in order for this group to be able to go home immediately, this person's not allowed to have the disease, this person's not allowed to have the disease, etc. And when does that happen? Well, if we know the probability of having the disease up front, let's say it's 1%, well, and that can be translated to a probability of 1 minus p, that the first person doesn't have the disease, and you would get the same number for all the people in the group. However, I'm not interested in just a single person, I'm interested in the entire group, and that would mean that I would have to multiply all of these probabilities together, because the first person's not allowed to have it, and the second one, and the third one, etc. And here's why I need to introduce a second variable, and I'll call it g. Let's say that g is the group size, the size of the group. And the reason why I'm introducing it, really, is just to save on ink. Let's say that I had a group of 10 people, then if I wanted to write down a probability for that entire group, well then, I would need to write this multiplication 10 times. Whereas if I just know that I have a parameter g that I can use for that, then the formula becomes 1 minus p to the power of g. We are now at a very interesting point in time. We have calculated something that we are interested in, but at the moment it's just a formula, which is rather formal, and that's great because it gives us structure, but it doesn't necessarily give us something that's interpretable. So before diving further, I think it's a good idea to now take this knowledge and to apply some programming to make some charts and some interactive visuals that allow us to understand the dynamics at play here. What you see here is a Jupyter notebook. And what I'm going to do is I'm going to take this formula that we derived earlier, and I'm going to play with it by introducing some charts and widgets. So what I've done is I have created this long array called G. It represents a number line that starts at 1, that ends at 200, and has 200 steps in between. And the idea is that for every point on this number line, I can calculate the associated probability. And I can do so using this formula over here. You can see that I'm doing this in the code over here. I am assuming that there's a probability of 1% to have the disease. These two multiplication symbols in Python means to take something to the power of. And what this will do is this will give me two arrays, one with the group size and another one with the calculated probability values. And let's show what that looks like in a chart. And here's what that looks like. On the x-axis over here, we've got the group size. And on the y-axis here, we've got the probability that nobody in the group has a disease. From the chart, you can again confirm that there is this balance. If I have a group size of 25 people, then roughly there's an 80% chance that no one in that group has the disease. And if I go for 100, that probability is a fair bit smaller. But again, you could argue that there might be a balance still. In this case, yes, I would need to be a little bit lucky in order for the entire group not to have the disease. But in the case below, here I would have a smaller group. So sure, the probability would be more interesting, but I would need 4 of these in order to have one of these. So there's still a balance at play. So that makes me think that I want to evolve this chart. And here's my logic. If my group size is 50 people, then it seems like there's a 60% chance that all of those people can go home. So what I kind of want to do is I want to multiply my group size here with the likelihood that they can just all go home. If I have my group size and my probability value, effectively what I'm going to do is I'm going to take every value g over here, multiply that by every probability value over here, and that's going to give me a new number that I would like to plot against the group size. So I'll add that code now and I'll run it. Here you can see the new chart that has the multiplication. Note that the group sizes on the x-axis correspond with each other, but we get a chart now that has a slightly different shape. So let's see if we can interpret this chart. In the previous video, we made this new chart, but we were still investigating what the meaning of it might be. This chart is telling me that if I have a group of size 100, that there's a 40% chance that that group can go home. That doesn't tell me how many people can go home on average, though. So the chart over here shows this number multiplied by the corresponding number on the y-axis. So that means that now here I can say, if I have a group of size 100, then on average there are about 36 people that don't need to be retested. Another thing that's interesting about this chart that makes it different than this one is that this chart seems to have a hump. There seems to be this optimum. And that's pretty interesting because that suggests that there might be an optimal group size that we can pick. So let's explore this chart a little further. I have redrawn the chart. You can see it below over here, but I've made it a little bit more fancy. Using this library called IPyWidgets, I am now able to add this slider. And whenever I change this slider, the chart below here will update. The slider that you see represents the probability that a single person would have the disease. Right now it's at 4%, but what I could do is I could move it down a little bit. Now, you'll notice that the shape of this curve changes, but the main thing that's happening here is that this optimal hump, this place where we have the highest point of the curve, that's pointing to a fairly large number now. If I were to instead move it to the other direction, then we see that the optimal value, the place where the hump is the highest, is much closer to 0. And if I were to think what this means, it's something that makes sense. If it's very likely that you're going to have the disease, then we probably should be making much smaller groups. And if it's very unlikely that an individual would have the disease, well then we can afford much larger groups. That's what this interactive visualization is telling me. There's also something else that it's telling me. It seems that where the optimal value is depends a lot on the probability. What it doesn't depend on, though, is the number of people that I need to test in total. And that's pretty interesting, too. As a next step, what I would like to do now is I would like to maybe calculate some sort of an optimum. I would like to be able to say, given that I have some sort of a probability value, what's the optimal size for my group? I would like to approach this mathematically, but as we'll see in a moment, Python has tools to actually help us do this math right. Usually when you're dealing with code, you are dealing with objects that represent data and/or charts. But Python also has this tool that allows you to play around with mathematical constructs. The library is called Senpai, and we're going to be playing around with it for this part. I just ran the code that's in this cell. In the cell, I'm saying that there are symbols, which you can see as mathematical variables. And what you can do is you can use these symbols to construct an expression. And what you're seeing here is the formula that we started out with. And now we've got this object in Python that represents that expression. And just to review,
this is the number of people in the group, and this is the probability that all the people in the group do not have a disease. Now, what you might remember from high school mathematics is that when you have an expression or a function, let's say it has this shape, and you're interested in figuring out where there is this optimal value, well, then you're looking for the place where there's a slope that's equal to 0. Because at some point, the function's going up, and at some point, the function's going down, but it's exactly at that point where it's not going down yet where we've got ourselves an optimum. We can double check that this optimum is indeed a maximum value by confirming that the second derivative is negative. And you might remember that we have to do this because that means that after we've reached this point with no slope, the slope that follows is negative. We could do all of that grunt work with maths on a piece of paper on this formula, but the cool thing about Senpai is that it can just do that for you. I can tell Senpai to differentiate this expression with regards to g. The next thing that I got to do is I got to solve for this expression being equal to 0. Now, the reason why we're interested in this, again, is because when we've got our maximum, we should have a slope that is equal to 0. Also, this math is something that you don't have to do. Senpai can do that for you. We take our differentiated expression, and then we solve that with regards to g, which means that we're asking it, hey, could you solve that for 0? And there we go. If we know the probability of getting the disease, then this will be the optimum value for the group size. We can even do the second differentiation here. We differentiate something that gives us an expression. We differentiate that again. And then again, we solve for g. And here we've got an expression that's negative. So we just used Python to do all of the mathematical grunt work, and now we have a formula that, given a probability that someone has the disease, gives us the optimal size for grouping people together. And that's really nice. If you're a little bit rusty when it comes to differentiating or integrating, Senpai can really help you out. We can even go one step further. What I've done is I've taken the expression that Senpai calculated and I've written it down below. And that means that I now have an expression for my optimal group size. What I can do now is I can substitute 1% as the value for p. And this suggests that if the probability is equal to 1%, that my group size needs to be 99 people. And when it's 2%, it's got to be more like 50. Let's double check if we did the math right by confirming this with the slider chart that we made earlier. I'm back at my slider chart, and I'm going to move the slider now to have a value that's 1%. And pay attention to where this hump moves. It's tricky to eyeball, but yeah, it feels like we are at 99 or close to 100 at least. And let's now move the slider up to 2%. And when we do that, yep, we are much closer to 50. So it seems like we did our math right. Now, kind of the meta thing I was hoping to show in this video is just how useful it is if you can do just a little bit of programming inside of an interactive environment, mainly because it allows you to not only double check yourself, but also because it just makes the whole exercise that much more intuitive. One thing I do want to mention is that you shouldn't worry too much about the code that's in front of you. If you're new to programming, you might not recognize everything that's happening here, and that's completely fine. All of these code examples can be downloaded later, so you can play around and interact with these examples yourself at your own leisure. Let's now take a step back to consider the big mental picture again. At the moment, we have this formula that allows us to go from a probability that one person has the disease to some sort of optimal group size. What we gotta do now is wonder, well, how is this going to evolve when we do this testing over multiple rounds? For all intents and purposes, let's say that we have a population and we're splitting up our population into different groups according to our formula, well then what's going to happen is that some of these groups are going to be just fine because no one in there had a disease. But we might have a couple of groups that still had the disease, which would imply that these groups of people would need to be retested. In this new round, though, there's a couple of things that are different, if you think about it. Let's say we had 1,000 people first, and let's say that our initial probability was 1%. Then you would expect that out of these 1,000 people, about 10 had the disease. We also just learned that those 10 people were not in this group, so that means that they will need to be here. We can still expect the same number of cases, but we can now expect these to appear in a subset of our original population. So that means that at the start of this new round, our probability has to update. If we assume that we have half the people that we had before, then the probability should double. Because we have a new probability value though, that also means that our optimal group size also updates. And because the probability value is much higher, we now probably have to resort to much smaller groups than we had before. And as you might be able to imagine, this process is only going to be repeating itself until at some point we might be able to assume that most of the people left have the disease and that they should each individually get tested. Now, I don't know about you, but I find this whole system to be very satisfying intellectually because something that I did not anticipate is happening here. Notice that in order to find the most optimal way to find these groups, it doesn't matter how big the starting population is. It doesn't matter if it's 1 million people or 100 million people. The strategy for finding the optimal group to reduce the tests that you need only depends on the probability of getting the disease. To demonstrate this, I wrote a little simulation that allows me to play around with some parameters that help explain what's going on. What you see here is a Python object that implements everything that I mentioned earlier. The maps for the optimal group sizes in here, as well as the probability updating within rounds. And because you can find the implementation of this object in the show notes, I won't bore you with the implementation details here. Instead, what I would like to do is just have a look at the logs that come out of the simulation, because there's an interesting lesson here. The simulation that I'm currently running has the probability of a disease of 1% and an initial population size of 1 million people. In round 0, nothing's happened yet. We can argue that there should be about 10,000 cases in this population size. We've not done any tests yet. We've not determined a group size for this round yet, but we do have this estimated probability. This probability is used in the next round to come to a optimal group size. Groups are made, tests are performed, and eventually we are left with a subset of the entire population. We are able to send a couple of people home, but because all of our cases are now in a smaller population subset, we have to update our probability value for having the disease. And this process just repeats, and repeats. We use the probability here to get a new group size. Again, people can go home, which in turn means we get a new probability value, which again means that we can update the group size. And we keep doing this, and we keep doing this, until at the end we have a couple of tests that we've performed, and we have a much smaller population. But because the number of cases is still the same, the probability just skyrockets, and at some point we could say, well, let's just test everyone here. There's something interesting, though, that we could do. You could wonder, well, what happens if I just make the population size much bigger? What will change? Let's make it 10 times as big. When I make it 10 times as big, sure, the numbers here change, but it kind of feels like the probability values that I get out over here don't. Also here at the end, I have a situation where almost 55% of the population that's left has a disease. At every round, it seems like we're able to send about a third of the people home, no matter how big our starting population is. It really seems like you only need 13 rounds to properly test everyone, and you could do it for a fraction of the population size. Something that I find intellectually satisfying about this mathematical system is that it really seems that the optimal strategy for assigning people into groups doesn't really depend on a population size. I mean, sure, it has to be much bigger than the group size that we come up with over here, but besides that constraint, this could be 100,000 people, 1 million, 10 million, but the optimal strategy really only depends on this. In this series of videos, we've been playing around with this thought experiment. This thought experiment, which I should stress, doesn't necessarily reflect reality, but nonetheless, it's a thought experiment that I found to be very satisfying intellectually. We're dealing with a system here that doesn't really depend on the size of a population that you're testing. It turned out that the main thing that matters is the probability that a single individual in the population will get the disease. And that's something I wouldn't have guessed up front, but it's certainly something that intrigues me in hindsight. The main thing that I really like about the act of doing this analysis, though, is that it proves a bigger point that's a bit more meta. You see, I think I could have gotten to the same conclusion if I were just using the very formal, more mathematical way of thinking about the system. Similarly, I also think I could have gotten here by just programming. Doing everything with simulations and applying some numerical tricks likely would have also gotten me to this same conclusion. But I really do think the journey was way more satisfying because I've been able to switch around between these two, I suppose, ways of thinking. Mathematics really gives you structure and direction, where interactive programming really gives you insights and intuition. And what I really hope is that the people who consider themselves more trained in the mathematical field are maybe just a little bit more willing to consider some of the tools from Jupyter and Python and to look into adding that to their tool belt. Similarly, for those who are a bit more versed in programming, I really hope that I've been able to show you some tools that might make investing a little bit more knowledge into mathematics less intimidating. There really are tools like Senpai that can help out, especially when you're learning. And if I might suggest a final idea, if you're interested in learning, if you're really interested in getting this exchange going, then maybe you shouldn't focus too much on the tool that you're interested in learning. Instead, what you might want to do is go out there in the real world and try to find another thought experiment like this one. If you want to learn a new tool, it might also be good to look for a problem that suits that tool very well. Otherwise, you're just learning syntax. So if you're going to be trying to pick this up, just try to look out there in the real world for an interesting thought experiment that might allow you to apply something that you already know, but also to learn something that you didn't before.